So now I'm back to the PowerPoint slideshow right where I left off. Um, Now I wanted to go through a few quick exercises of creating a sampling distribution with a small population of only 4 people to help make the idea of a sampling distribution a little bit more concrete. So if I had, imagine that there's a population of 4 people. Maybe it's a family of 4 people or a group of 4 friends, and each person has a value. Maybe this is the height of each person, and um, let's say that these are the heights of the 4 people. And as a researcher, I want to take a sample of 2 people from this population and calculate the mean height of those 2 people to estimate the mean height of this entire population of 4 people. And I know it doesn't seem realistic because if the population has only 4 people, why wouldn't I just select all 4 people? But I mean, why wouldn't I just collect data from all population members? But this this actually isn't meant to be realistic. This is just meant to be a demonstration of the idea of a sampling distribution. It's just an exercise. So if I selected 2 people out of these 4 and recorded their heights, these would be the possible samples of 2 people that I might end up selecting. I might end up getting person 1 and person 2 and recording their heights. I might get 1 and 3. I might get 1 and 4. I might get 2 and 3. I might get person 2 and person 4, or I might get person 3 and person 4. So if I randomly selected 2 people to be the sample, these are the 6 possible samples, and I'm going to end up getting one of them to be my sample. Each possible sample of 2 people has its own sample mean. You can find it by adding the 2 numbers and dividing by 2. So if you add these 2 heights and divide by 2, you get this number. If you add these 2 heights and divide by 2, you get that number. Remember, x bar is sample mean, so it's just the mean of the sample. And the population mean, which is mu, would be the mean of all 4 population members. If I added their 4 heights and divided by 4, I would get the population mean. So here's the sampling distribution for a sample size of 2. If I'm selecting a sample of 2 people from this population, there's 6 possible samples, and each one has its own sample mean. And these 6 sample means in here make up the sampling distribution for the sample size of 2. And the mean of the entire population, if we calculated it, would actually be 57. That's the mean of all 4 people. If I added these 4 numbers and divided by 4, I would get 57. So we can see that 2 samples have a sample mean that's perfectly equal to the population mean. 2 samples have sample means that are below the population mean. They underestimate the population mean. 2 of the possible samples have sample means above the population mean. So these 2 samples overestimate. So we're just seeing the idea of sampling variability right here. Here, if I was taking a sample of 3 people from this population, recording their 3 heights, these would be the 4 possible samples. I would end up getting one of these 4 possible samples to be my actual sample. And the way I created these possible samples is just by leaving one person out of each sample. So here I left out person 4, here I left out person 3, here I left out person 2, and here I left out person 1. That's how I created these 4 possible samples. Each possible sample has its own sample mean. You can find it by adding 3 numbers and dividing the total by 3. So if I selected 3 people from the population, recorded their heights, and calculated the sample mean as an estimate of the population mean, then one of these 4 sample means would end up being my sample mean that I actually used to estimate the population mean. This might be my sample mean if I get sample 1. This will be my sample mean if I get sample 2. This will be my sample mean if I get sample 3. So here's the sampling distribution. If there's 4 possible samples, and the means of those 4 samples that I listed out here make up the sampling distribution. All I did was I took the 4 sample means over here and listed them in a column. So these 4 sample means all make up the sampling distribution. All 4 of these x bars make up the sampling distribution over here. Now let's discuss the mean and standard deviation of a sampling distribution, because a sampling distribution is really just a list of numbers, so any list of numbers has a mean and standard deviation. The mean of the sampling distribution is always equal to the mean of the population, regardless of the sample size. That's something we'll look at in a second. So the sample means are always centered at the population mean. So let's take a look at that. Here, if we add the 4 values in the population and divide by 4, we get the population mean, which is 57. The population has a mean height of 57. If we add the 6 sample means over here and divide the total by 6, we get the mean of the sampling distribution, which is also 57. So I said that the population mean and the mean of a sampling distribution always come out to the same number. And the symbol for the population mean is mu, but the symbol for the mean of the sampling distribution is actually mu x bar, because it's the mean of all of the sample means. Remember, x bar is sample mean. So let's look at a visual of this. Here's the 4 heights of the 4 population members, with the population mean at the center. Here's the 6 sample means in the sampling distribution, with the mean of 57 at the center. So the population is centered at 57, because that's the population mean. And the 6 sample means are also centered at the population mean. And we can see that this side of the sampling distribution has sample means that underestimate the population mean. This side of the sampling distribution has sample means that overestimate the population mean. But it's roughly half underestimate and half of them overestimate, because the population mean is at the center. Now let's look over here. If we add these 4 numbers and divide by 4, we get the mean of the other sampling distribution, which was the means of all possible samples of 3 people. Once again, the mean of the sampling distribution equals the population mean. I said that the population mean and the mean of the sampling distribution are always the same number, regardless of what sample size you're dealing with. So it's 57 again. Once again, we can see that just like how the population has the population mean at the center right here, the sampling distribution of sample means also has the population mean at the center. But since we're dealing with a sample size of 3 now, since each of these sample means is now a mean of 3 people instead of just 2, the sample means are now closer together. They're more packed in toward the population mean of 57. So the population had the most spread. The means of the samples of 2 people had less spread, and the possible samples of 3 people, their means had the least spread of all. So when we go from here to here to here, we're looking at less spread. But all 3 of them have 57 and have a population mean of 57 at the center, because they all have the same mean of 57. Like I said, they don't all have equal dispersion. This has the most dispersion. This has the least dispersion. And there's actually a value that measures the amount of dispersion or the amount of spread in a sampling distribution, and it's called the standard error. So, and I'll talk about the standard error next. The standard error is really just the standard deviation of the sampling distribution. Remember, the standard deviation measures the spread of a set of numbers. So the standard deviation of the values in a sampling distribution have a special name called the standard error, even though it really is just a standard deviation. So the standard deviation of these 6 sample means would be called a standard error because these 6 numbers make up a sampling distribution. The standard deviation of these 4 numbers would also be called the standard error. So the standard deviation of the sampling distribution is the standard error. It measures how spread out the sample means are from each other. So here's, if we actually wanted to calculate the standard error, we would just plug in the standard deviation formula and just get our answer just using the standard deviation formula. This right here would be the standard error of these 6 sample means in the sampling distribution over here. And it's really just a standard deviation, but it's called a standard error. It's called a standard error because it's not a standard deviation of people, it's a standard deviation of sample means. These 6 numbers over here are all just sample means. If we plugged in the other sampling distribution, which included the means of the 4 possible samples of 3 people, it would be another standard error. Remember, this was the mean of 3 people, this was the mean of 3 people, and this was also the mean of 3 people, and this was the mean of 3 people. The standard deviation of these 4 values would also be called the standard error. So it's called, the standard error is 0.7. So here, well, the standard deviation of the people in the population is just called the population standard deviation sigma, and it's 2.24. So these 4 heights have a standard deviation of 2.24. The standard deviation of these 6 sample means is called the standard error, and it came out to 1.3. The standard symbol for standard error is sigma x bar, because it's the standard deviation of the sample means. These 4 values had a standard error of 0.7. And you can probably see why these 6 numbers had a higher standard error, and these 4 numbers had a lower standard error, because these 6 sample means of all possible samples of 2 people are more spread out, so they have a bigger standard error. These 4 sample means of all possible samples of 3 people have less spread, which is why they have this smaller standard error. So when the sample size goes up from 2 to 3, the standard error drops, because the sample means move in closer together. And the reason why this idea of a standard error is important is because when a researcher takes a sample from a big population and calculates the sample mean to estimate the population mean, and if the researcher uses a small sample size, the means of all of the possible samples will be more spread out with a bigger standard error, and the researcher is likely to get a less accurate sample mean further from the population mean at the center. But if the researcher takes a bigger sample from that population and calculates a sample mean, then all of those possible samples that could be selected have sample means that are closer together, more moving in closer toward the population mean. So the researcher is likely to get a more accurate sample mean in that situation. So if I was interested in estimating the mean income of Pleasant Hill, and I take a sample of 10 people, and I calculate the mean of and I record their 10 incomes, and I calculate the mean of my sample to estimate the population mean, the standard error will be big, because all of the possible samples of 10 people that I could get will all have, they'll have widely different sample means, like we see here, and I could get a sample mean that's way off from the population mean. But if I take a sample of, let's say, 100 people from Pleasant Hill and record their incomes, and I calculate the sample mean, the mean of my 100 people is likely to be more accurate, closer to the population mean, because all of those possible samples of 100 that I could get from Pleasant Hill will have sample means that are closer together toward and close to the population mean that I'm estimating. So I'm likely to get an accurate sample mean in that case. So when I use it in a study, when I use a bigger sample size, the standard error is smaller because the possible samples that the researcher could get have sample means that are closer together and closer to the population mean. So you want to use a big sample size if you can, so that the standard error will be small, and you're likely to get a sample mean close to the population mean. You don't want the possible samples to have high dispersion like they have here. You want them to have low dispersion like they are here. Also, if a study is repeated over and over again, and a different result is calculated each time, then, well, if a small sample size is used and the standard error is big, what ends up happening is the results change a lot from one study to the next. They bounce around a lot. So if I keep sampling 2 people from here over and over again, and I calculate the mean, and each time I take 2 people, I calculate the sample mean, my sample means will change more from one outcome to the next. Sometimes I'll get 55. Sometimes I'll get 59 up here. Sometimes I'll get 55 again. Sometimes I'll get 56 again. But with if you use a bigger sample size and the standard error is smaller, then the results don't change as much from one study to the next. Because if I kept on sampling 3 people from this population over and over again and calculated the mean each time, sometimes I'd get this, sometimes I'll get this, but overall, my results will be more consistent from one outcome to the next. It'll be more like this. Because if the possible samples are closer together, like they are here, the results will be more similar from one study to the next. If the possible samples are more spread out, you have less consistent results from one study to the next. So when the sample size is bigger, the standard error is smaller, which means the possible samples have sample means that are less spread out. And also, when the study is repeated over and over again, the results will be more consistent from one outcome to the next. And I showed you a couple examples of calculating a standard error with the standard deviation formula, but in an actual study, you can't calculate the standard error that way because you don't actually have a list of all possible samples like I did. You don't know what all those possible samples are, so there's actually a formula that's used in an actual study to get the standard error. What it is the standard deviation of the people in the population standard deviation, divided by the square root of the sample size you're using. The sample n is a symbol for sample size. So if I'm taking a sample of 30 people from the Pleasant Hill population and recording their incomes, and I'm calculating the sample mean to estimate the population mean. And like I said, if I'm taking 30 people, if I divide the standard deviation of Pleasant Hill incomes, the population standard deviation, by the square root of 30, which is the sample size that I'm using, I will actually get a standard error of my study, which is the standard deviation of the means of all possible samples of 30 that I might end up selecting to be in my study. In other words, I'll get the standard error of the sampling distribution that I'm drawing from, which in my case would be all possible samples of 30. And if I'm, once again, I want the standard error to be small because that means that the possible samples are more similar and more accurate.